Hello everyone, and welcome to this video on Newton's second law with systems. So as a refresher, systems are collections of one or more objects that we're going to focus on analyzing as a whole. We're going to ignore properties and interactions internal to the system and focus on interactions between the system and its surrounding environment. So a pretty common example of systems that we would analyze with forces in physics would be things that are connected by a string that pass over a pulley. So we'll draw an example here of a cart that's on some horizontal surface, and it's attached to a hanging mass, and it's attached with a string that passes over this pulley. So the hanging mass can move in the vertical direction while the cart can move in the horizontal direction. Since the string and the pulley are considered lightweight and ideal, we're going to assume that they have negligible mass and that they're going to not really contribute to the acceleration or the motion of the system. This is an assumption that we'll make to simplify the problem, but we can look at situations where the string has mass or where the pulley has mass or non-negligible friction. The environment to the system is anything that we're not looping in the system. So that would be the earth and the horizontal surface, both of the horizontal surfaces, the floor, and the one that the cart is on. So Newton's second law modified to analyze systems is just that the acceleration of the system is equal to the net external force on the system divided by the mass of all the objects in the system. And this is assuming that the objects all move in unison in the system. So to use this approach, we're going to consider the direction of acceleration to always be the positive direction. So forces that are in the same direction of the acceleration are positive, whereas forces opposing the direction of acceleration are negative. And here are the steps to analyze using this modified system. So we want to enclose our system in a loop or a blob. We want to draw and label the forces acting on the whole system and whose agents are external to the system. So we want to focus on those. And then we want to use this equation: acceleration of the system is equal to the net external force divided by the mass of the whole system. So in this example of block A stacked on top of block B, we could group them as a whole system and say it's just the system of block A and block B. The external forces on this system would be the gravitational force acting on the entire mass of the system, so A and B, and the normal force acting upwards on the system. So we'll take a look at an example problem where we have one of those carts on a horizontal surface that's attached by a string passing over a pulley to a hanging mass. Now here we actually have some values of masses. We get that the cart's mass is 2 times m naught, and the hanging mass is just simply m sub 0 or m naught. And we want to derive an expression for the acceleration of the whole system. And we want to express our answer in terms of the value of the mass that they give us, m naught, and physical constants as necessary, meaning we're allowed to have the variable m subscript 0, and we're allowed to have physical constants in our final equation, but nothing else. We don't need to necessarily use all of those, but in this example we will. So we're going to draw a loop around our system, and then we're going to draw any external forces or forces coming from the environment on objects in the system. So we know that gravity is pulling down on both objects. It's pulling down on the 2 mass object by 2 m naught times g, and it's pulling down on the hanging mass by m naught times g. On the 2m, or on the cart, there's also a normal force pointing up. And just to note here, we do have forces on these objects from tension, but tension is internal to the system because it's inside of our blob. So now we've enclosed our system in our loop or a blob, and we've drawn and labeled the forces on the system from the surrounding environment. So now we're going to use acceleration of the system as the net external force divided by the mass of the system. One thing we can note here is that the normal force on the cart and its weight force, the 2 m naught times g, are going to cancel out. So they're actually not going to affect the acceleration of the system. And the only external force that's going to affect the acceleration is this weight force of the hanging mass. So plugging in our values, we're going to get, in the numerator, we're going to get m naught times g divided by the mass of the hanging mass, m naught, plus the mass of the cart, which is 2 times m naught. So we get m naught times g divided by 3 times m naught. So we see that the 2 variables m subscript 0 are going to cancel out, and the acceleration of our system is just simply the gravitational acceleration divided by 3. And so notice, even though the problem asks us to express our answer in terms of m naught and physical constants as necessary, we don't actually need to use all the terms, and we're not using the m term that's here. So our answer meets these requirements and we're good to go. So the systems approach is pretty beneficial, but it does have its pros and cons. So the pros are it ignores all the internal interactions, it gives us a quick approach to find the acceleration, and it helps develop this ability to recognize external forces. But it doesn't really give us any information about what's going on inside the system, and it doesn't work if the objects aren't moving in unison. And that's it on this video, introducing Newton's second law with systems.